First of all, I would like to thank the organizer for giving me the opportunity to present today. My presentation will be about robustness evaluation and application examples of the VIVA Plus models. I will start by giving a motivation why we have created the VIVA Plus models. Then I will introduce the models, and finally I will switch over to the main topic of today. That is model robustness. How do you make models robust during the development phase? And how do we then test that the models are robust? First, do we really need another human body model? When we discussed this in a virtual project, we identified some important topics. The first topic is inclusion. It has been shown in many studies that females are at greater risk to sustain injuries, and this is true for most body regions and crash configurations. However, when we look at available female human body models, there is only the 5th percentile female. The major problem is that she only represents a small fraction of the females. So designing countermeasures for this size does not necessarily benefit the whole female population. The second topic is model transparency. Today's proprietary models have encrypted parts, meaning that you do not have to access the full model. Similarly, you do not have access to the validation data, meaning that you cannot check the assumptions of the setup or confirm the results. Other human body models are provided free of charge without encrypted body parts, but have user agreements that limits the possibility to share the models and prohibits its use for some applications. The third topic is about granularity. The major human body models of today exist in several versions, from simplified versions for kinematic assessment and injury assessment based on global injury criteria to detailed versions for tissue-based injury criteria. If you want to use tissue-based injury criteria, you need to use the detailed version, which is typically quite CPU intensive. The fourth topic is also about inclusion, but inclusions of all road users. All road users here mean that in addition to models of vehicle occupants and pedestrians, we also have riders. We have riders of various two-wheelers, passengers in public transport, and possibly more modern things like e-scooter riders. However, we also want to consider that people come in different sizes and shapes, and for this we usually use mesh morphing. And then finally, the main topic of today, model robustness. The human body is quite complex to model, both in terms of geometry and material characterization. The main challenge is robust and biofidelic modeling of soft tissues. Looking through the literature, there are many publications reporting numerical issues of human body models, resulting in incomplete parameter studies. So what have we done for the VIVA Plus models? As an inclusion statement, the first model we created was the average size female, instead of the average size male that traditionally is the first model in human body model families. This model is also the base model where all the development is carried out, and more on that later. To ensure maximum transparency, the VIVA Plus models have no encrypted parts. In addition, all validation load cases, including post-processing scripts, are openly available, so you can download and rerun this on your system. This also means that it's possible to ensure that the models give the same results on your hardware. Based on biomechanical principles, any countermeasure should apply external forces to the strong skeletal parts of the body. That is why we have modeled the skeleton in great detail, but used simplified modeling of soft tissues. For example, no detailed modeling of the internal organs. To make it easy for end users to use the model for different applications, we have created versions representing many road users, in addition to the in-vehicle occupants and pedestrians. However, the numerical robustness is the main topic of today, and I will come back to how we address this in the modeling phase as well as in the testing phase later in this presentation. The VIVA Plus models, their validation catalog, and the documentation is available under different open source licenses on the openvt.edu platform. This means that it's possible to freely share the content, either alone or together with your vehicle model. It can also be noted that the models can be used for any application, including military, even though that it's not developed and validated for this application. The validation catalog is documented in Jupyter Notebooks. For you who don't know what that is, a Jupyter Notebook can be seen as an advanced text document where it's possible to include calculations. Maybe some of you have used MatCAD, which is a similar commercial alternative. Dinosaur, which is based on Python code, is used for post-processing. This process makes it possible to easily rerun all validation load cases when a new version is available. Some skeletal body parts have been modeled in greater detail to enable tissue-based injury criteria. The first part is the rib cage that is modeled in a similar way as in the safer HBM. The cortical bone is modeled with shell elements and the trabecular bone and intercostal muscles with solid elements. The thickness of the cortical bone is based on average values from the literature. The bones in the lower extremities are modeled using only solid elements, as the cortical bone is much thicker compared to ribs. The femur shaft have 3 elements of the thickness, while the tibia and fibula have 2. The current model of the knee ligaments use pre-stressed discrete elements. We are, however, working on a more refined version using solid elements for the ligaments as well. The pelvis is modeled in a similar way as the ribs, with shell elements for the cortical bone and solid elements for the trabecular bone. Also here, the thickness of the cortical bone have been mapped from measurements of biological data. The pelvis have been further updated and validated in the SafeUp project. In addition, in the OSCAR and SafeUp projects, a new lumbar spine have been developed with the intention to predict compressive fractures on tissue level. Specifically, the spongeous bone is modeled with an orthotropic material model and injury risk curves are under development. The model have been integrated into the seated female VIVA Plus model, but is not yet published in the main branch on OpenVT. The upper extremities are modeled in a similar way as the lower extremities. However, as the upper extremities was not the focus in virtual project, the model of these bones are currently not validated. As mentioned earlier, the base VIVA Plus model is the seated average female. The geometry is based on statistical shape models, and actually it's based on the same geometry as the newly presented Hermes models presented at Arcobi and developed by Amtri. From this base model, 3 derivative models are created using mesh morphing by means of a custom morphing script. Additionally, some post-processing is performed to guarantee that the element quality as well as contact definitions match the base model quality. The main difference between a base model and the derivatives is the nodal coordinates. This means that the model enhancement updates are done. When they are done, this can rather quickly be disseminated to the derivative models. Here we see an illustration of morphing the base model to the derivative models. If we look carefully, we can see that it's not a pure scaling. For example, the ribs in the rib cage have steeple angles for males, which is included in a morphing. Another quite visible change is the forward rotation of the pelvis when morphing from seating to standing postures. Based on the derivative models, repositioned models have been created, representing standardized pedestrian and cyclist postures. For example, postures according to TB24 are available, and I can also mention that the models have been certified for TB24. If you would like to reposition any of the models into another posture, Piper metadata have been created. In addition, Beta is currently working on metadata for the latest VIVA Plus model for positioning also in the ANSA preprocessor. So far, 3 papers on the validation have been published and 2 additional are in manuscript form. Much of the content of the current presentation can be found in the Hello World paper. By the end of the year, we will have 13 component validation tests published on OpenVIPT, and these will range from validation of single bones to tabletop tests. In addition, 15 full body validation tests will be published. These include omnidirectional in-vehicle occupant validation as well as pedestrian impact validation. Generally, we try to run both pre-positioning and impact in one seamless simulation to make it easy to rerun the validations when a new model is available. You can see examples of this here, where the pre-positioning is carried out during the first 300 milliseconds and then followed by the impact. Now, let's switch to the specific topic of today. First, what can we do to maximize our chance of having a robust model? As users of explicit finite element codes, you're probably aware that the root cause of numerical crashes are usually related to either the poor mesh, improper contact definitions, or improper material definitions. So, to maximize the chance of having a robust model, we should create a high-quality mesh, have accurate and efficient contact definitions, use robust material definitions, and to some extent we can also play with the element formulations. Preferably, we should use quad and hexahedral elements to maximize speed and accuracy. In particular, we should use this in parts where we want to evaluate injury on tissue level. In order to do this, we have used a hexablock design in ANSA preprocessor. We have used some predefined element quality criteria that you can see to the right, and we have made sure that 100% of the elements fulfill these criteria. In addition, we had one person doing all the mesh. This is of course time inefficient, but we decided that this was the best approach as all parts of the body is interconnected. So changing the mesh in one end of the body can influence the mesh in the other end. In total, we ended up with about 4,000 connected hexablocks in the half model before reflecting over the symmetry plane. And here we can see that we have a very good mesh. The solid red bars represent the baseline model, and the other bars the derivative models. We can see that the morphing to derivative models only marginally reduce the mesh quality. More than 97% of the elements have a Jacobian over 0.7, an aspect ratio less than 6, and over 90% of the elements have warping less than 6. For the contacts, the general strategy was to have as few contacts as possible and try to avoid tight contacts if possible. This means that we used nodal connectivity instead of contacts if possible. An example is the connection between the femur and the soft tissue around. In addition, we tried to make the contact surfaces smooth and continuous, for example, by including an abdominal wall and a pelvic floor. Finally, all models are fully depenetrated. That means no intersections or penetrations. So when we run the models, we should not have any contact warnings in the output files. The general strategy for material models was to use well-proven and numerically fast material models. We have mainly used the Ogden material model for soft tissues and piecewise linear plasticity or plasticity tension compression for modeling bones. We also try to use material parameters that always result in stable solutions. An example is to avoid using too many parameters to fit the shear modulus in Ogden material. Using many parameters might give a perfect fit for the low strain level used during fitting, but there is a risk that this might lead to negative material stiffness when loading the material further, which in turn can lead to instabilities. Also, we have not implemented element erosion. One particularly successful material implementation is the one that we used for fat tissue. This one is based on work by one of my former PhD students, Hossein Nasseri, and despite being a very soft material, the implementation is numerically stable. Generally, we have used fully integrated elements where we want to evaluate injury risk and under-integrated elements for soft tissues undergoing severe deformation. This makes the models numerically robust, as under-integrated elements can undergo much more deformation than fully integrated elements. But the drawback is that we have quite a lot of hourglass energy, which is not optimal. So how do we check that the models are robust? In my opinion, the best way to make sure that the models are robust is to run large parameter studies. The different loading parameters will trigger many different numerical problems in the model, if we had such. When I did my PhD, I created a generic parameterized vehicle interior and I ran 1000 simulations with an early version of the safer human body model. After the first iteration, I had many error terminations. Then, compiling the root cause of all these terminations, I discovered that we had a few problematic areas in the model. I did some updates, and after a couple of iterations, I had a model that were much more robust. Based on this, we created a small subset of severe impacts, exercising different parts of the model. We always run these robustness load cases after each model update. I have now shared this generic vehicle interior on OpenVT under open source. So if you like to test this way of evaluating model robustness, you can download this model. I can also mention that this generic interior model has been used in several projects, both in Europe and North America. In addition, we test the robustness of the pedestrian models using a generic vehicle front. Also, this model can be found on OpenVT if you like to download and test your own human body model. As an extreme load case, to the right here, we can see a pedestrian being impacted at 90 km/h. This simulation actually ended up in an error termination, but very late after the peak loading. The VIVA models have been used in some parameter studies during the virtual project. The first example is a parameter study on vehicle passengers subjected to 4 different impact configurations. In addition to crash configuration, the posture and seat position was also varied, resulting in a matrix with 48 simulations. From a robustness perspective, all the 48 simulations terminated normally. 2 additional parameter studies were carried out using the repositioned pedestrian and cyclist models. One using a vehicle-specific model and one using a generic vehicle front. Vehicle impact speed were varied up to 50 km/h. Using the generic vehicle model, all 550 simulations terminated normally, and using the vehicle-specific model, all but 2 simulations terminated normally. Finally, one parameter study with a tram impacting a pedestrian in different configurations and at different speeds, up to 60 km/h, was carried out in the virtual project. In total, 72 simulations were carried out and all terminated normally. To summarize my presentation, an open source human body model family, including a validation catalog, is available for free at openvt.eu. We have used detailed modeling of the skeleton to enable tissue-based injury evaluation. The models have already from start been developed with robustness in focus, and we continuously monitored the robustness using some severe impacts. In the end, the models have proven to be numerically robust in parameter studies including in vehicle occupants, pedestrians and cyclists impacted by cars, pedestrian impacted by tram. And finally, please download the model, have a look, and tell us what you think. The model can be found on openvt.eu, and if you like, you can use the link provided on this page. Thank you for listening.